Okay, in the previous lecture, I defined the Laplace transform and why we need a Laplace transform, and the fact that complex exponentials are eigenfunctions, right? And I defined the Laplace transform x of s as integral x of t e raised to minus st dt, right? And remember, here we are playing with signals x of t, which may not necessarily satisfy the Dirichlet conditions. It may not be absolutely integrable, right? So the question is, what is the guarantee that this integral actually converges? So what's the guarantee that we can evaluate this integral? The answer is actually there is no guarantee that this integral converges, but actually there is no guarantee that the integral converges for all values of s, but it may converge for some values of s. Well, I'll give you an example, and then we'll talk about what I mean by the region of convergence and stuff like this. I think it's best when it's introduced through an example. So suppose x of t is equal to e raised to at u of t. Okay, I'm not necessarily restricting myself to a being less than 0. So a could be greater than 0 in this case. Okay, and let's assume that a is real. It's not a big deal if a is not real, but let's first assume that a is real. So what's the Laplace transform for x of t? It's integral minus infinity to plus infinity e raised to at e raised to minus st u of t dt. But since I have a u of t, I can simply replace the lower limit here by 0 and say this is integral 0 to infinity e raised to a minus s t dt. Okay, so now comes the question as to when does this integral converge. Okay, now notice this. S is sigma plus j omega, right? So e raised to a minus s times t is equal to e raised to a minus sigma times t times e raised to j omega t. So this is actually nothing but a complex exponential, where this determines the frequency and this pretty much determines whether it's a growing exponential or a decaying exponential. So if this is a decaying exponential, then I can perform this integration, right? This becomes absolutely integrable. But if it's a growing exponential, then this integral does not converge. So this integral converges as long as a minus sigma is smaller than 0, right? Because then it would become a decaying exponential. Or equivalently, sigma is greater than a. Or equivalently, the real part of s, sigma is nothing but the real part of s, right? The real part of s is greater than a. Okay, and in this case, it's quite easy to evaluate what x of s is, because it's a minus s times t divided by a minus s between 0 and infinity. And if this condition is true, if it is true that a minus sigma is smaller than 0, then when I plug in t is equal to infinity, I'm going to get 0 for the upper limit, right? Because it's a decaying exponential that has decayed to 0. Whereas in the lower limit, when t is 0, I get 1. So I get minus 1 minus a minus s, which is equal to 1 over s minus a, But for this to be true, we need the real part of s to be greater than a. So what we would say is that the Laplace transform of e raised to at u of t is 1 over s minus a. But this alone is not enough. We need to say that the real part of s has to be greater than a, right? Because if the real part of s is not greater than a, then the true definition of the Laplace transform is not the same as this. So that is why, so this condition saying the real part of s is greater than a tells you in which region of the s-plane the integral actually converges. So we call this as the region of convergence. Now this is the one difference that we'll have to deal with here that we did not have to deal with in the Fourier transform. So the region of convergence is the region in the s-plane where the Laplace transform converges. Okay, this will be called the ROC, the region of convergence. So for this particular case, what was the region of convergence? So the region of convergence is all points s for which the real part of s is greater than a. So if you look at the s-plane, we already drew the s-plane with sigma on the x-axis and omega on the y-axis. So this region of convergence will be a half plane to the right of s, where this is a. Right, because it's defined by all points for which the real part of s is greater than a or sigma is greater than a, or equivalently. Okay, so it's always important to specify the region of convergence in addition to the Laplace transform when we are dealing with the Laplace transform. I'll tell you why this is important for another reason. Turns out that you can have different signals whose Laplace transforms are actually the same, although the two signals are different. However, it will turn out that the region of convergence of the Laplace transform will be different in both cases. Okay, again, this is best explained with another example. Suppose I look at another signal, say y of t. It's equal to minus e raised to at u of minus t. Okay, how does the signal look before we compute the Laplace transform? Here's a u of minus t, so the signal is defined only for negative values of t. Right? For negative values of t, this is it has e raised to at, and if a is greater than 0, then this is a signal that decays like this. Right? Okay, let's compute the Laplace transform of this signal, but we're not going to assume that a is greater than 0 here. A can be greater than 0 or less than 0. So what is y of s? Y of s is integral minus infinity to plus infinity, negative e raised to at, e raised to minus st, u of minus t dt. But since I have a u of minus t, I can replace the the lower limit is negative infinity and the upper limit is 0. So now this becomes negative integral from infinity to 0 e raised to a minus s times t dt, which is negative e raised to a minus s times t divided by a minus s. Oops, negative infinity. So negative infinity to 0. But I can do this by swapping the limits. Okay, now now we have to be careful to see when this integral will converge, right? Okay, so in order for this integral to converge, so what am I going to do? I'm going to substitute t is negative infinity in the upper limit. So what I want is I want e raised to minus a minus s times negative infinity to be bounded to be 0. This means I need a minus s, the real part of a minus s, to be greater than 0, or a minus the real part of s to be greater than 0, or the real part of s must be smaller than a. So if this is true, then e raised to minus a minus s times infinity would be 0, and so y of s would be equal to 0 minus 1 divided by a minus s, which is 1 over s minus a. Notice that this is exactly the same as what we got here, 1 over s minus a, although the two signals are very different. X of t is actually e raised to at u of t. It's a right-sided signal. But y of t, on the other hand, is a signal which looks like this. It's a left-sided signal. So, but both of them have the same Laplace transform. The difference, of course, is in the region of convergence. Here, we want s to be, the real part of s to be smaller than a, whereas there you have the real part of s to be greater than a. Okay. Actually, another intuitive way to think about this region of convergence is roughly something like this. Um, actually, I will explain it like this. So remember, um, we define the Laplace transform as x of t times e raised to minus st dt, which is x of t times e raised to minus sigma t times e raised to minus j omega t dt. If I define this as a new signal, if I define x of t times e raised to minus sigma t as a new signal, and let's see if there is a term that they've given for this. No. So let me just call this as x sigma of t. You can see that the Laplace transform x of s is actually nothing but the Fourier transform of x sigma of t. Right? So essentially what we are doing is this. Saying, okay, if I want to evaluate the Laplace transform of x of t, I'm going to first take x of t and I'm going to multiply it by e raised to minus sigma t. And then I'm going to take the Fourier transform of the product of x of t and e raised to minus sigma t. The point is this: if x of t has growing exponentials, then we cannot talk about the Fourier transform directly of x of t, right? But if I multiply x of t by e raised to minus sigma t, then x of t times e raised to minus sigma t becomes something that's better behaved, or it may become integrable, so that I can talk about the Fourier transform of this signal. And that's pretty much all we have done. The region of convergence tells you, well, how much do I have to, or how should I choose my sigma in such a way that x of t times e raised to minus sigma t will have nice properties so that we can talk about the Fourier transform of these signals. Right? So to go back to the example and interpret it, if we looked at, let's take okay, maybe we'll take a numerical example instead of having a abstract a. Suppose I had the signal x of t is e raised to 2t u of t, right? So e raised to 2t is clearly a growing exponential, so we cannot talk about the Fourier transform of this. But we just computed the Laplace transform of x of e raised to at u of t, and that turns out to be 1 over s minus a, in this case is 2. But we said that the region of convergence is that the real part of s must be greater than 2, right? Alright, so what does this mean when the real part of s is greater than 2? When the real part of s is greater than 2, it means sigma is greater than 2. So we can think of the Laplace transform as saying, okay, I'm going to take my signal x of t first, and I'm going to multiply it with some e raised to minus sigma t. And in this case, sigma is greater than 2. So when I multiply x of t by e raised to minus sigma t, now I've created a signal which is a decaying exponential, right? Because x is, let me not use x of s here. So x sigma of t is e raised to 2 minus sigma t, and sigma is greater than 2. So this is a decaying exponential. And we can define the Fourier transform of a decaying exponential, right? That's easy to do, and that's really what x of s is in this case. Okay, this is why we have to have a region of convergence where the real part of s is greater than 2. And just to finish off the other example, suppose we had chosen an x of t which is, say, e raised to 2t u of minus t, negative e raised to 2t u of minus t. Okay, all right. Now, what is the region of convergence for this? Well, the region of convergence for this is that the real part of s is less than 2. Okay, this means I can take x of t. See, notice that in this case x of t is actually very well behaved. It's already a decaying exponential. Okay, so in principle I can directly compute the Fourier transform of this, and that's fine. Okay, but just to work the example out, what this essentially tells you is this, is that I can take x of t and multiply it with any e raised to negative sigma t, as long as sigma is less than 2. Okay, so I have a signal of the form e raised to negative sigma t, e raised to okay, so what do I get now? Now I get negative e raised to 2 minus sigma times t u of minus t. So notice that the signal is left-sided. It's defined only for t less than 0. So which means what I would really like for the signal to be integrable is that 2 minus sigma should be, what do I want it to be? I want it to be positive, right? So what it tells you is, well, you can take x of t, and of course this is how we got the condition that sigma has to be smaller than 2. Okay, so what it tells you is actually you can even, so for example, what let's do is a couple of quick things as examples, and you'll see what I mean. Suppose sigma is equal to 0. Okay, what does this mean? This means my s is equal to j omega, in which case the Laplace transform is the same as the Fourier transform. So this is okay. Sigma is equal to 0 is in the region of convergence. And so what it says is, look, I could have already talked about the Fourier transform of this signal because it was a well-behaved signal. Which is correct, we know that. But it tells you, well, is more. The signal is already decaying exponentially, so I could have even multiplied the signal by e raised to negative t, and it would have still been okay. Remember, t is negative here, right? It tells you I could have chosen sigma to be equal to 1, and this would have still been fine. I could have still talked about the Fourier transform of x sigma of t. That's really what the region of convergence tells you. So if the region of convergence includes sigma equal to 0, then it means the Fourier transform for these signals already exist, and we could have directly worked with the Fourier transform. Okay. Okay, so let me quickly summarize what I've been saying so far. So this lecture has really been about the region of convergence. Okay, this is the region in the S-plane, or the values of sigma and omega for which the Laplace transform converges. It is possible for different signals to have the same Laplace transform, but their region of convergence will be different. So we must always specify a region of convergence along with the Laplace transform to uniquely identify the signal. Okay. All right. Now, before I conclude this lecture, I will just take a few minutes and talk about another very important idea, although we will not explore too much of this, is called Polesandzeros. So usually when you compute the Laplace transform of a signal, you will get the Laplace transform to be in some kind of a rational form. I mean, you've seen Fourier transforms which look like this, and in the same way the Laplace transform will look like this as well. It will be some rational expression in S, right? So this rational expression can be factored into things of this form. We can write this as a product of m terms, each being of the form s minus ck times s minus dk. n factors in the denominator. So the values of s for which x of s is 0 are called zeros of x of s. That's kind of obvious, right? So in this case you can, so the values of s for which x of s is equal to 0 are called the zeros of x of s. So clearly here the zeros are ck's, right? Because when s is equal to ck, then x of s is 0. Now the values of s for which x of s is infinity or the denominator of x of s is 0, called poles. So in this case, the poles are decays, right? So it's common to have a pole zero plot. Um, so for example, where we plot the poles and the zeros in the complex x plane. Suppose I had a transfer function x of s, which was, let us say, s. So let's say it's s plus 1 times s minus 1 plus j times s minus 1 minus j divided by s minus 3 plus 2j times s minus 3 minus 2j. Suppose this is the transfer function. Then of course the zeros are at s equal to minus 1, 1 plus j, and 1 minus j. And the poles are at 3 plus 2j and 3 minus 2j. So we can draw a pole zero plot. It will be a plot in the s-plane where all the zeros will be denoted by circles and the poles by crosses. So 2, 3 plus 2j and 3 minus 2j. So these will be the poles. This is the s-plane. Okay. I think I will stop this lecture here.